This is chapter 4, number 74. 74 is a baseball question where, so you're an outfielder and you're here, and you want to get to home plate. And the first time you do it, you throw and it never bounces. And the second time you throw it, it goes and then it bounces. Okay, and you want to decide which actually got there faster. So both the distances is the same. So let's call the not bouncing at all, that distance is x, and it's the same thing as x1 plus x2, where x1 is the first part of the bounce, and then x2 represents after the bounce. Okay, so we have that relationship. And the other thing that says that after the bounce here, so after this bounce, the velocity goes from v to v naught over 2. So it loses half of its speed on the bounce. Okay? For most of this, and the first angle we throw with, the no bounce, is the angle of 45 degrees. And our goal is to find the other angle. Okay? So theta 1 is 45, theta 2 is that unknown. That's actually what we want to figure out. What angle do we throw it at if it's going to go, bounce, lose half of its speed, and still get to the same distance on that? We're going to use the range equation a lot. So the range equation is v naught squared sine 2 theta over g. And really what we're going to do is we're just going to set this and kind of solve. So that the total range is just this. V naught squared sine 2 times 45 over g, and we know that sine of 90 is just 1, so it's really just v naught squared over g. We're going to set that equal to x1. Well, x1 is launching in at the same speed at some different angle, theta 2 over g, and that's how far x1 is, but we're going to add that to x2. Well, x2 is launched essentially, relaunched after the bounce at half the speed, and it is going to reflect at that same angle, theta 2. So whatever the original one was thrown at, it's going to bounce, and it's going to bounce at that same angle over g. Okay? All of them have a g. All of them have a v naught squared. This is going to be a half, so this is just going to be sine of 90, but that's just 1. This is sine of 2 theta, and that's theta 2. And this is plus, think about this, this is a half that got squared, so it's a fourth. So that's 1/4 sine 2 theta 2. So that's just 1 equals 5/4 sine of 2 theta 2, which is the same thing as 4/5 equals sine of 2 theta, and then take inverse sine and then divide by 2, and you can figure out, hey, that angle, the other angle you can throw it at to bounce one time and go the same distance, is 26.6 degrees. Now, the flight time is a little harder. The flight time, we'll just to figure out the time, and it always goes back to using symmetry. So if you think of vertical velocity, we have that standard equation that vertical velocity is v naught sine theta minus gt. Makes sense. How fast it's going vertically. Subtract what gravity does, 9.8 meters per second squared, for that certain amount of time. But if we want to know max height, at max height it's 0, which leads us to this, which says that the maximum height, T max, the time it takes to get to max height, is just v naught sine theta over g. Well, we can double that to then find flight time, okay, and only in symmetrical cases. So now we say that we want to look at 1 bounce to 0 bounce. Okay, the 1 bounce is going to have 2 separate times. T1, right, and it's just this, doubling that, 2 v naught sine theta 2 over g, plus the other one is 2 v naught over 2 sine theta 2 over g. That's the time, it's both of their times together, and divide by 0 bounce. 0 bounce is just 2 v naught sine theta 1 over g. And again, think about that. I'm just using this equation. If it takes v naught sine theta over g to get to t max, then t flight, meaning the total flight time, is just double that. And I just did that for each of the paths. This represents the total flight time going at 45 degrees, right, theta 1. This represents the time it takes to do x1. You threw it at v naught sine theta 2 over g, and this one it bounces at half the velocity. So the original launch velocity of this flight time has to be half. All of these things are going to cancel to a pretty good ratio, and you end up just getting this ratio to be 0.95, which means one bounce is actually faster, right? This number is smaller than this number, and you get that ratio. So it's 95% of the time. So throwing it one bounce makes sense. Now maybe it's harder for the catcher to catch it. Maybe it actually doesn't bounce and get back to half of its speed. Maybe the angle it bounces with isn't the same. So in real life this may not be different. But under these assumptions, throwing a baseball with one bounce to the catcher actually gets there faster.